black holes, where time stops forever, Hawking radiation and the information paradox. What if you could fall forever? What if time itself could stop, not metaphorically but literally, frozen at the edge of a black hole while the rest of the universe ages billions of years in seconds? What if space-time could die, and everything you are could be compressed into a point of infinite density? Could the universe's darkest mystery hold the key to understanding reality itself? Welcome back to Sleep Entangled, where cosmic mysteries and tranquility merge into contemplative voyages. If you find wonder in these explorations of the universe's most extreme phenomena, remember to subscribe and let curiosity guide your nights. Now, settle in, breathe slowly, and let's drift together toward the edge of space-time itself. Chapter 1. The Point of No Return. Event Horizons. Imagine standing at the edge of a waterfall. The current grows stronger as you approach. At first, you could swim back to safety, but there comes a point, a line in the water, where the current becomes too powerful. Cross that line, and no amount of swimming will save you. You will go over the edge. A black hole has such a line. It's called the event horizon, the boundary beyond which nothing, not even light, can escape. The event horizon isn't a physical surface. You couldn't touch it, couldn't see it as you crossed it. It's simply the mathematical boundary where the escape velocity equals the speed of light. Inside this boundary, space-time itself is so severely warped that all paths lead inward, toward the singularity at the center. Outside the event horizon, you could theoretically escape if you had enough energy. Fire your rockets hard enough, and you might break free from the black hole's gravitational grip. But cross that invisible line, and escape becomes not just difficult, but impossible. Forbidden by the very geometry of space-time itself. This is what makes black holes fundamentally different from any other object in the universe. A planet has strong gravity, but you can always escape if you're fast enough. A neutron star's gravity is crushing, but light still escapes from its surface. Only at a black hole does the universe draw a line and say, beyond this point there is no return. The size of this boundary was first calculated in 1916 by German physicist Karl Schwarzschild, just months after Einstein published his theory of general relativity. Remarkably, Schwarzschild found this exact solution to Einstein's equations while serving in World War I, dying of illness shortly after. The Schwarzschild radius, the distance from the center to the event horizon, depends only on mass. Compress any amount of matter into a small enough space, and it will form a black hole. For a black hole with the mass of our Sun, the Schwarzschild radius is about 3 kilometers. Shrink the Sun down to a ball just 6 kilometers across, and it would become a black hole. For Earth, the radius would be only 9 millimeters. Compress our entire planet into a sphere smaller than a marble, and space-time would close around it like a trap. Supermassive black holes at the centers of galaxies have event horizons millions of kilometers across. The black hole at the heart of our Milky Way, called Sagittarius, a star, has an event horizon about 12 million kilometers in radius, roughly the distance from the Sun to Mercury. Yet despite this enormous size, it contains 4 million times the mass of the Sun, all compressed into a region of space-time from which nothing can escape. Why is escape impossible once you cross the event horizon? The answer lies in how black holes warp space-time. Imagine space-time as a fabric. Mass creates curves in this fabric, gentle dips around planets, deeper wells around stars. But a black hole creates something more extreme, a pit so steep that it becomes vertical, then turns inward on itself. Outside the event horizon, Space-time curves toward the black hole, but outward paths still exist. Light can still escape, carrying information about events near the black hole to distant observers. Inside the event horizon, all paths lead inward. There is no outward anymore. Every direction you could travel, every path through space-time leads you closer to the singularity. It's not that the black hole pulls so hard you can't escape. It's that the structure of space-time itself eliminates escape as a possibility. The future, your future, points inward. To escape, you would need to travel into the past, and that's forbidden by the laws of physics as we understand them. The event horizon creates a profound barrier for information. Everything that falls past it is cut off from the outside universe, not just physically, but informationally. This creates one of the deepest mysteries in physics. According to classical general relativity, once something crosses the event horizon, no information about it can ever reach the outside world. The black hole simply grows slightly more massive, slightly larger, but the universe loses all detailed knowledge of what fell in. A star that collapses into a black hole carries with it information, the positions and velocities of every atom, the quantum states of every particle. Where does that information go? Does it vanish forever, or is it somehow preserved? This question, which we'll explore in depth later, touches on fundamental principles of quantum mechanics and leads to what physicist Stephen Hawking called the greatest crisis in physics. Physicists sometimes describe event horizons as one-way membranes in space-time. You can pass through in one direction, inward, but never return. Light and matter flow through this membrane easily, but nothing flows back out. This one-way property has strange consequences. If you watch someone fall toward a black hole from a safe distance, you would never see them cross the event horizon. As they approached, they would appear to slow down, their image growing dimmer and more red-shifted as their light struggled against the black hole's gravity. Eventually, they would seem to freeze just above the horizon, their image fading to black as the light they emit becomes infinitely stretched. But from the perspective of the falling person, nothing special happens at the event horizon. They cross it smoothly, falling inward at increasing speed, experiencing nothing but the growing tidal forces that will eventually tear them apart. The horizon isn't a wall or a boundary they can perceive, just a point of no return that they pass without noticing until it's too late. Imagine standing at this ultimate threshold. Behind you, the universe you know, light, information, the possibility of return. Before you, a darkness so complete that not even light can climb back out. The event horizon doesn't mark the end of space, but it does mark a boundary in time. Cross it, and your future is sealed. You will meet the singularity. There is no other option, no escape, no reprieve. It is the universe's most absolute one-way door, a threshold that divides what can be known from what must remain forever hidden. In the next chapter, we'll explore what happens to time itself at this boundary, and why, from a certain perspective, you might fall forever without ever quite crossing. Chapter 2, where time stops and space begins. Time is not constant. This was Einstein's revolutionary insight, proven countless times through experiment. Clocks run faster at higher altitudes, slower in strong gravitational fields. Near a black hole, this effect becomes extreme. Imagine two observers, one safely far from a black hole, the other steadily approaching the event horizon. Both carry identical atomic clocks, perfect timekeepers that measure the passage of seconds with exquisite precision. To the distant observer watching through a powerful telescope, the approaching clock appears to tick slower and slower. As the falling observer nears the horizon, their clock seems to nearly stop. Each second they experience takes longer and longer to pass from the distant observer's perspective. At the horizon itself, time appears to stop completely. This isn't an illusion or a limitation of observation. It's a genuine feature of how time flows differently in different gravitational fields. A phenomenon called gravitational time dilation, predicted by Einstein's general relativity and confirmed in countless experiments. From the perspective of someone far from the black hole, anyone falling toward it will never quite reach the event horizon. They'll appear to slow down asymptotically, approaching but never crossing, their image frozen forever at the boundary like an eternal photograph. This creates a strange picture. From outside, the event horizon becomes a graveyard of frozen images. Every atom, every photon, every piece of matter that ever fell toward the black hole, all seemingly suspended at the surface in a state of eternal approach. But here's the paradox. From the perspective of the infalling observer, nothing special happens at the horizon. Their clock ticks normally. They cross the boundary in finite time, perhaps in seconds, perhaps in minutes, depending on the black hole's mass, and continue falling inward. Both perspectives are equally valid. Time is relative. There is no universal now that all observers agree on. The falling observer experiences the crossing. The distant observer never sees it. Both descriptions are true within their own reference frames. Inside the event horizon, something even stranger occurs. Space and time exchange roles. Outside the black hole, you can move freely through space. Forward, backward, left, right, up, down. But time flows in only one direction, forward into the future. You cannot move backward in time, only deeper into what's ahead. Inside the event horizon, this reverses. Space becomes one-dimensional, pointing inexorably toward the singularity. You cannot move left or right, cannot change your spatial trajectory. All spatial paths lead to the center. But time becomes negotiable, at least mathematically. The singularity isn't a place in space that you travel to. It's a moment in time that you travel toward. Just as you cannot avoid tomorrow by standing still, you cannot avoid the singularity once you've crossed the horizon. It lies in your future as surely as next Tuesday, and you will reach it whether you like it or not. Physicists use diagrams called light cones to visualize how space-time works. At any point in space and time, imagine a cone extending into the future. This represents all the places you could possibly reach if you travel at or below the speed of light. Similarly, a cone extending into the past shows all the places from which light could have reached you. In flat space-time, far from any massive objects, these cones point straight up and down through time. You have freedom to move anywhere within the future cone, bounded only by the speed of light. Near a black hole, these cones begin to tip inward, tilted by the warping of space-time. As you approach the event horizon, the cones tip more and more, until at the horizon itself, the edge of the future light cone points directly toward the singularity. Inside the horizon, the entire future light cone points inward. There is no path through space-time, not even at the speed of light, that leads back out. The singularity lies in everyone's future. It is as inevitable as the next moment. As you fall toward a black hole, you begin to feel tidal forces, differences in gravitational pull between your head and your feet, or between your left and right sides. Near a stellar mass black hole, one formed from a collapsed star, these tidal forces are catastrophic. Long before you reach the event horizon, the difference in gravity between your head and your feet becomes so extreme that you would be stretched like taffy. elongated into a thin stream of atoms. Physicists call this spaghettification, a term both whimsical and horrifying. For a black hole with the mass of the Sun, spaghettification would begin thousands of kilometers from the event horizon. Your body would be torn apart, stretched into a strand of atoms, then pulled apart at the atomic level, then at the nuclear level, until you were reduced to a stream of elementary particles falling inward. But here's something remarkable. For a supermassive black hole, the kind with millions or billions of solar masses, the tidal forces at the event horizon are gentle. The horizon is so far from the center that the gravitational gradient is relatively mild. You could cross the event horizon of a supermassive black hole and survive, at least temporarily, experiencing nothing more than weightlessness and perhaps a strange sense of falling. Of course, you still couldn't escape, and eventually, as you fell deeper, the tidal forces would grow until they tore you apart. But for a brief time, you could exist inside a black hole, conscious and aware, experiencing a region of space-time cut off from the universe you knew. Let's think about this more carefully. To an outside observer, you're frozen at the horizon, never quite crossing, your image slowly fading to black, as the light you emit loses energy climbing out of the gravitational well. But in your reference frame, you cross smoothly. Time flows normally for you. You see the universe outside racing forward, stars aging, galaxies evolving, perhaps even seeing the far future of the cosmos compressed into the moments before you're torn apart. Some theoretical calculations suggest that as you cross the horizon, you might briefly see the entire future history of the universe flash before you, a final gift from relativity, showing you eons of cosmic evolution in your last seconds of existence. This dual description, frozen outside, falling inside, is one of the deepest puzzles in black hole physics. Both views are correct, yet they seem contradictory. Resolving this paradox requires understanding not just gravity, but quantum mechanics, information theory, and perhaps the very nature of observation itself. So as you drift into rest, imagine time itself as a river. Far from the black hole, the river flows gently, carrying you forward at a steady pace. As you approach the horizon, the river seems to slow, time stretching like honey, each moment lasting longer than the last. And at the horizon, from outside, time appears to stop. A perfect stillness, an eternal moment. But if you could ride that river across the boundary, you would feel no change in flow. The current would carry you forward as always, smooth and inevitable, until you reached the singularity where time itself ends and the river pours into something we cannot yet describe. Next, we'll explore what it would actually feel like to approach a black hole, and why the tidal forces that tear matter apart hold clues to the deepest structure of space-time. Chapter 3, Spaghettification, Tidal Forces at the Edge. Tidal forces are, at their heart, differences in gravitational pull across space. On Earth, you feel them subtly. The Moon pulls slightly harder on the side of Earth facing it than on the far side, creating ocean tides. Near a black hole, this same principle becomes violently extreme. Imagine floating toward a black hole feet first. Your feet are closer to the black hole than your head, so they experience stronger gravity. The difference is slight at first, barely noticeable. But as you fall closer, the gradient steepens. Your feet are pulled harder, your head less so. You begin to stretch. This isn't a gentle stretch. For a stellar mass black hole, one with a few times the Sun's mass, the tidal forces grow so strong that they would overcome the electromagnetic bonds holding your atoms together. You wouldn't just be pulled apart, you would be unraveled at the molecular level, then atomic, then nuclear. The process has been given a deceptively playful name, Spaghettification, but there's nothing playful about having your body elongated into a stream of particles, stretched into an ever-thinning thread as you fall toward the singularity. The strength of tidal forces depends on the black hole's mass and the distance from its center. Remarkably, larger black holes have gentler tides. For a black hole with the Sun's mass, the tidal forces at the event horizon would create a difference of about 100 billion Gs between your head and feet if you were 2 meters tall. That's 100 billion times Earth's gravity, enough to tear apart not just flesh and bone, but atomic nuclei themselves. But for a supermassive black hole, say 1 billion times the Sun's mass, the tidal forces at the event horizon are only about 1/10,000th of Earth's gravity. You could cross the horizon and barely feel it. You might experience a sensation like falling, perhaps a mild discomfort, but nothing immediately lethal. This is one of the profound ironies of black holes. The bigger they are, the gentler they are at their boundaries. A small black hole will tear you apart before you even reach the event horizon. A supermassive one will let you cross peacefully, only killing you later as you fall deeper toward the center. Long before astronauts might risk falling into black holes, we can observe tidal destruction on cosmic scales. When a star wanders too close to a supermassive black hole, tidal forces can tear the star apart in an event called tidal disruption. The critical distance where this occurs is called the Roche limit, the point where tidal forces overcome the star's own gravity. For a star like our Sun approaching a million solar mass black hole, this happens at about 100 million kilometers from the center, well outside the event horizon. This star is stretched into a stream of hot gas, forming an accretion disk that spirals inward. As the gas falls, friction heats it to millions of degrees, causing it to emit intense X-rays. Astronomers have observed dozens of these tidal disruption events, watching stars get spaghettified in slow motion over weeks or months. These events are beautiful in their violence, stellar material streaming away in long arcs, glowing brilliantly before plunging past the point of no return. They're also scientific gold mines, allowing astronomers to study both the properties of black holes and the interior composition of stars torn open like cosmic fruit. Here's a thought experiment. Suppose you could survive spaghettification somehow. Perhaps you're made of some exotic material immune to tidal forces. What would you see and feel as you fell? At first, far from the event horizon, space would look nearly normal. The black hole would appear as a dark sphere against the stars, its gravity bending light around it in a bright ring called the photon sphere. As you fell closer, the black hole would seem to grow, filling more and more of your visual field. The light from stars behind you would be blue shifted, compressed to higher frequencies as you fell toward them. The light from stars ahead, toward the black hole, would be red-shifted, stretched to lower frequencies. The event horizon itself would remain invisible. There's no glowing surface, no warning sign. You would cross it without fanfare, noticing only that the black region in your vision now encompassed half the sky, then more, then nearly everything. Throughout all this, you would feel the tidal forces. If you were falling into a stellar mass black hole, those forces would long since have torn you apart. But in a supermassive black hole, you might feel only a gentle stretching, a pulling along your length, stronger at your extremities than at your center. Eventually, no matter the black hole's size, the tidal forces win. As you approach the singularity, the gravitational gradient becomes infinite. The difference in force between your head and feet, or between any 2 points separated by any distance, grows without bound. At this stage, spaghettification isn't just a metaphor. you truly would be reduced to a string, a one-dimensional line of particles stretched so thin that the distinction between you and the space between your atoms becomes meaningless. Current theory suggests that before you reach the singularity itself, quantum effects would become important. Perhaps you wouldn't be stretched infinitely, but would instead reach some quantum limit where the very notion of position and size breaks down. Perhaps space-time itself becomes granular at these scales, made of discrete units too small to stretch further. But these are speculations. No one knows what happens in the final moments before reaching the singularity. It's a region where general relativity predicts its own breakdown, where quantum mechanics must play a role, but where we lack a complete theory to guide us. If you could somehow observe the process from a safe distance inside the event horizon, an impossibility, but let's imagine, you would see space itself flowing inward like a river toward a drain. Light travels along this flowing space, and near the singularity, space flows inward faster than the speed of light. Light itself cannot escape, not because it's moving too slowly, but because the space it travels through is rushing inward faster than light can travel through it. It's like trying to swim upstream in a river flowing faster than you can swim. No matter how fast you move, you're carried backward. Similarly, inside a black hole, space itself falls inward so fast that even light is carried toward the singularity. This is why the singularity is inevitable once you cross the horizon. You're not just falling through space. Space itself is falling, and you're falling with it. So as you settle deeper into calm, imagine yourself not stretched and torn, but gently elongated, like a brushstroke pulled across a canvas. Picture your consciousness not destroyed but transformed, spread across the fabric of space-time itself, becoming part of the black hole's structure. In this visualization, spaghettification is not violence, but metamorphosis, a change from being a localized thing to being distributed across space-time, woven into the very geometry of the universe. Let that image carry you softly forward as we prepare to explore what lies at the end of this cosmic elongation, the singularity itself, where space-time curves infinitely and the known laws of physics dissolve into mystery. Chapter 4. Inside the black hole, where physics breaks. At the heart of every black hole, according to general relativity, lies a singularity, a point where space-time curvature becomes infinite, where density becomes infinite, where the known laws of physics cease to function. A singularity isn't really a point in the usual sense. It's more accurate to say it's a place where our mathematical description of space-time breaks down. The equations of general relativity, which work beautifully everywhere else, produce infinities at the singularity, a sign that something is wrong, or at least incomplete, in our understanding. Imagine trying to calculate the surface area of a sphere as its radius shrinks to zero. The area gets smaller and smaller, but remains finite. Now imagine calculating the density of matter as it's compressed into zero volume. Density is mass divided by volume, and if volume approaches zero while mass remains constant, density approaches infinity. This is what happens at a singularity. All the mass that falls into a black hole is compressed into zero volume. Infinite density, infinite curvature of space-time, infinite tidal forces. Our equations break down because nature doesn't usually present us with infinities in physical quantities. Not all singularities are the same. A non-rotating black hole has a point singularity at its center, the simplest, most symmetrical case, described by the Schwarzschild solution to Einstein's equations. But real black holes rotate. They form from collapsing stars or merging objects that have angular momentum, and that rotation persists in the black hole. A rotating black hole is described by the Kerr solution, discovered by physicist Roy Kerr in 1963. In a rotating black hole, the singularity isn't a point but a ring, an infinitely thin circle of zero thickness but finite radius. This ring singularity has even stranger properties than a point singularity. For one thing, the mathematics suggests that you could pass through the ring without encountering infinite tidal forces. On the other side, you might enter a region of negative space-time curvature, a region that, according to the equations, could connect to another universe, or even to another part of our own universe. Of course, these are mathematical possibilities, not proven realities. Most physicists believe that before you could pass through the ring, quantum effects or instabilities would destroy you. But the mathematics is tantalizing, hinting at deeper structures we don't yet understand. Inside a rotating black hole, there's not just one event horizon but two. The outer event horizon, which we've discussed, and an inner horizon called the Cauchy horizon. The Cauchy horizon is even stranger than the event horizon. At the event horizon, you lose the ability to send information outward. At the Cauchy horizon, determinism itself breaks down. Beyond the Cauchy horizon, the future is no longer uniquely determined by the past. The equations of physics become ambiguous. Time travel becomes possible, at least mathematically. You could encounter closed time-like curves, paths through space-time that loop back on themselves, allowing you to meet your own past. Physicists debate whether the Cauchy horizon is physically real or just a mathematical artifact. Some argue that quantum effects would make it unstable, turning it into a singularity where space-time tears apart. Others suggest it might be traversable under certain exotic conditions. Roger Penrose proposed the cosmic censorship conjecture, the idea that nature censors naked singularities, always hiding them behind event horizons. If true, this would prevent us from ever observing the breakdown of physics directly. But it's just a conjecture, not a proven theorem, and physicists continue to search for counterexamples. The honest answer is, we don't know. General relativity predicts the singularity but cannot describe what happens there. It's like a map that says, "Here be dragons," a boundary beyond which our current theories cannot guide us. Several possibilities exist. First, perhaps the singularity is real, and matter is genuinely compressed to infinite density. In this case, our understanding of physics is incomplete, and new laws must govern what happens there. Second, perhaps quantum mechanics prevents the formation of true singularities. At extremely small scales, near the Planck length, about 10 to the negative 35th meters, quantum effects dominate. Perhaps space-time itself becomes grainy or foamy at these scales, preventing infinite compression. Third, perhaps singularities are wormholes, bridges to other regions of space-time or other universes. This is highly speculative, but mathematically consistent with general relativity. Fourth, perhaps black holes don't have singularities at all, but instead have something else at their core, a region of highly compressed but finite density matter held up by quantum pressure or exotic physics we haven't discovered yet. Here's where things get truly puzzling. According to quantum mechanics, information cannot be destroyed. If you burn a book, the information in it isn't lost, it's scrambled into the smoke, heat, and ash. Given perfect knowledge of the final state, you could, in principle, reconstruct the book. But what happens to information that falls into a black hole? According to classical general relativity, it vanishes at the singularity, lost forever. The black hole retains only three properties: mass, charge, and angular momentum. All other information about what kind of matter fell in, its quantum states, everything that makes it unique is gone. This seems to violate quantum mechanics. Physicist John Wheeler summarized this with the phrase "black holes have no hair," meaning they have no distinguishing features beyond mass, charge, and spin. Everything else is erased. But in the 1970s, Stephen Hawking discovered that black holes aren't entirely black. They emit radiation, and over time they evaporate. When the black hole finally disappears, what happens to the information? This is the black hole information paradox, one of the deepest unsolved problems in theoretical physics. We'll explore it in depth in later chapters. In 2012, physicists Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully proposed a radical idea. Perhaps the event horizon isn't empty space, but a firewall, a region of intense energy that would incinerate anything trying to cross it. This idea emerged from attempts to resolve the information paradox. If information must escape from black holes, perhaps it does so through Hawking radiation, but for that to work, the radiation must be entangled with the black hole's interior in a way that seems impossible without violating other principles of quantum mechanics. The firewall idea is controversial and not widely accepted. Most physicists believe there's a way to resolve the paradox without invoking such a dramatic violation of general relativity's predictions. But the fact that serious physicists even consider it shows how profound the puzzle is. One intriguing resolution to the paradox comes from the holographic principle, which we'll explore in Chapter 9. This principle suggests that all the information about the black hole's interior is encoded on its event horizon, like a hologram, where a two-dimensional surface contains information about a three-dimensional object. If this is true, then information isn't destroyed at the singularity. It's preserved on the horizon, somehow encoded in the quantum structure of spacetime itself. This idea has profound implications, suggesting that spacetime itself might be emergent, not fundamental, but arising from deeper quantum information structures. So as you rest, imagine the singularity not as a point, but as a question mark, a place where the universe itself pauses, uncertain how to describe what lies within. It's the cosmic equivalent of dividing by zero, where mathematics gives up and says, "I don't know." Perhaps that's fitting. Perhaps the universe needs places of genuine mystery, regions where knowledge ends and wonder begins. The singularity is physics' way of saying, there's more to reality than equations can capture, more to existence than what we can measure and predict. Let that mystery carry you gently forward, as we turn to one of the most beautiful discoveries in modern physics, Stephen Hawking's revelation that even black holes, the darkest objects in the universe, can glow. Chapter 5. Hawking radiation, when black holes glow. Empty space, it turns out, isn't truly empty. According to quantum field theory, the vacuum is alive with activity, virtual particles constantly popping into existence in matter-antimatter pairs, existing for the briefest instant before annihilating each other and vanishing back into the quantum foam. These aren't real particles in the usual sense. They exist for such short times that they cannot be directly observed, but their effects are real. They contribute to measurable phenomena like the Casimir effect, where two metal plates placed close together in a vacuum experience a tiny attractive force due to virtual particles. Near a black hole's event horizon, this quantum vacuum becomes the key to one of the most remarkable predictions in theoretical physics. In 1974, a young British physicist named Stephen Hawking was studying the quantum behavior of fields near black hole event horizons. He made a discovery so surprising that he initially thought he'd made a mistake. He found that black holes aren't entirely black. They emit radiation. a faint glow of particles that leak away from the event horizon, carrying energy away from the black hole. Over time, this radiation causes the black hole to lose mass, slowly shrinking, gradually evaporating. The mechanism is subtle. Near the event horizon, virtual particle pairs are constantly appearing. Normally, these pairs would quickly recombine and vanish. But right at the horizon, something different can happen. Imagine a particle-antiparticle pair appearing just outside the event horizon. Sometimes, one member of the pair falls into the black hole while the other escapes. The escaping particle becomes real, flying away into space. The infalling particle has negative energy relative to distant observers, causing the black hole to lose mass. This process is called Hawking radiation, and it's a genuine quantum effect. It's not a classical phenomenon. It arises only when you combine quantum mechanics with general relativity. Considering how quantum fields behave in curved spacetime, Hawking radiation has a temperature inversely proportional to the black hole's mass. For a stellar mass black hole, say 10 times the Sun's mass, the temperature is about 0.00000006 Kelvin, far colder than the cosmic microwave background radiation filling space. This means stellar mass black holes are currently absorbing more energy from the universe than they emit. They're growing, not shrinking, because the universe is warmer than they are. But supermassive black holes are even colder. A billion solar mass black hole has a Hawking temperature of only 10 to the minus 17 Kelvin. A trillion times colder than the coldest temperatures ever achieved in laboratories. Only black holes smaller than about the mass of the Moon would be hotter than the current cosmic background radiation. Such small black holes, if they exist, would be actively evaporating. How long does it take a black hole to evaporate completely? The answer depends on its mass, but the timescales are staggering. A black hole with a Sun's mass would take about 10 to the 67th power years to evaporate. 10 trillion years. The universe is currently only about 13.8 billion years old, so a solar mass black hole would persist for an almost incomprehensibly long time. A supermassive black hole with a billion solar masses would take 10 to the power of 91 years, a number so large it's nearly meaningless. By this time, every star in the universe would have died, every galaxy dispersed, and only black holes and their faint Hawking glow would remain. But the process accelerates as the black hole shrinks. As it loses mass, its temperature rises, causing it to evaporate faster. In the final moments, a black hole radiates intensely, disappearing in a burst of high-energy particles and gamma rays. Hawking radiation creates a profound puzzle. The radiation is thermal, it has a temperature, but it's random, with no information about what fell into the black hole. Imagine you throw an encyclopedia into a black hole. All the information in that encyclopedia, the text, the images, the arrangement of atoms, vanishes past the event horizon. Over eons, the black hole evaporates into Hawking radiation. But that radiation is just random thermal photons and particles, containing no trace of the encyclopedia. Where did the information go? Was it truly destroyed? This seems to violate quantum mechanics, which says information is never destroyed, only transformed. In quantum theory, if you know the exact state of a system at one time, you can in principle calculate its state at any other time. Information is preserved, but if black holes destroy information, then quantum mechanics is wrong, at least in the presence of strong gravity. This contradiction is the black hole information paradox, and it haunted Hawking for much of his life. For decades, Hawking maintained that information was truly lost in black holes. He even made a bet with fellow physicists John Preskill and Kip Thorne that information was destroyed, wagering an encyclopedia on the outcome. But in 2004, Hawking conceded the bet. He announced at a conference that he now believed information was preserved, though he wasn't sure how. He gave Preskill an encyclopedia, a cricket encyclopedia causing some amusement, and admitted that the paradox had led him to reconsider his position. How could information escape? Hawking suggested that perhaps quantum fluctuations at the event horizon allow information to leak out gradually, encoded somehow in the subtle correlations of Hawking radiation. But this raises new questions. The radiation leaves the black hole from the event horizon. How does it know what's inside? How can information about matter deep inside the black hole, perhaps near the singularity, be transferred to radiation at the horizon? One promising answer involves quantum entanglement. When virtual particle pairs form at the event horizon, they're entangled. Their quantum states are correlated in ways that persist even when one falls in and the other escapes. Perhaps as matter falls into a black hole, it becomes entangled with these particles. As Hawking radiation escapes, it carries entanglement with the black hole's interior. The information isn't destroyed, it's encoded in the pattern of entanglement between the radiation and what remains of the black hole. This idea leads to the notion that black holes are fast scramblers, systems that mix information so thoroughly that it becomes nearly impossible to recover, but not truly lost. Given enough time and precise measurements, you could, in principle, reconstruct what fell in by analysing the Hawking radiation. Physicist Don Page calculated how entropy should evolve as a black hole evaporates. Initially, entropy increases as matter falls in and Hawking radiation begins, but at some point, the Page time about halfway through the evaporation, entropy should begin to decrease as information starts escaping. This creates a curve showing entropy versus time. For years, this Page curve seemed impossible to derive from physics, but recent advances in string theory and quantum gravity has shown that the curve can be reproduced, at least in certain simplified models. This is one of the strongest pieces of evidence that information is indeed preserved, somehow encoded in correlations we don't yet fully understand. One fascinating possibility: perhaps tiny black holes formed in the early universe shortly after the Big Bang. These primordial black holes would have masses much smaller than stars, perhaps just a few kilograms or tons. Such small black holes would be hot, radiating intensely. A primordial black hole with the mass of a large mountain would be completing its evaporation about now, after 13.8 billion years. Its final explosion would release as much energy as millions of nuclear bombs. Astronomers search for such explosions, but none have been detected. If primordial black holes exist, they must be rare, or perhaps they're all much more massive than the threshold for current evaporation. So as you drift into rest, imagine a black hole not as absolute darkness, but as a faint, impossibly cold ember, radiating softly, glowing with a light so dim it would take 1 trillion years to see with the naked eye, yet real, persistent, slowly carrying away the black hole's substance into the void. Every black hole is mortal. Even these cosmic giants, these tears in space-time, will one day fade away, returning their stolen mass to the universe as a gentle rain of particles and light. Nothing lasts forever. Not stars, not galaxies, not even black holes themselves. Let that thought carry you gently forward as we prepare to explore the deepest mystery of all. When a black hole evaporates, when it returns its mass to the universe, what happens to everything that fell inside? Chapter 6. The Information Paradox. Where did it go? Imagine you write down a secret on a piece of paper, fold it carefully and toss it into a fire. The paper burns, turning to ash, smoke, and heat. The secret seems destroyed, lost forever. But is it? According to the laws of physics, information is never truly lost. Every atom in the paper, every photon of light released, every molecule of gas in the smoke, all of them carry information about what was burned. In principle, if you had perfect knowledge of every particle's state after the burning, you could reconstruct the paper, the ink, and yes, even read the secret. This principle, that information is conserved, is one of the deepest laws of quantum mechanics. It's connected to the reversibility of quantum evolution, to the unitarity of quantum theory, to the fundamental structure of how we describe reality. But black holes seem to break this law, and that's a crisis. In the early 1990s, physicist Leonard Susskind proposed an idea called black hole complementarity to try to resolve the paradox. According to complementarity, there are two valid but seemingly contradictory descriptions of what happens when something falls into a black hole. From the perspective of someone falling in, they cross the event horizon smoothly and eventually reach the singularity. The information they carry goes with them, disappearing from the universe. From the perspective of someone outside, they never quite cross the horizon. Instead, they seem to hover just above it, their information gradually spreading across the horizon's surface and slowly leaking back out through Hawking radiation. Both descriptions are valid, Susskind argued, but they can never be compared directly. An outside observer can never follow someone inside to see which version is really true. The two perspectives are complementary. Like wave-particle duality in quantum mechanics, both are correct within their domains. Complementarity led to one of the most profound ideas in modern physics, the holographic principle. In the 1970s, physicist Jacob Bekenstein discovered that a black hole's entropy, a measure of how much information it contains, is proportional not to its volume but to the area of its event horizon. This was strange. For ordinary matter, entropy scales with volume. A bigger box of gas contains more molecules and therefore more entropy. But for black holes, entropy scales with surface area. Gerard 't Hooft and Leonard Susskind took this further, proposing that all the information about what's inside a black hole is actually encoded on its two-dimensional event horizon, like a hologram, where a three-dimensional image is stored on a two-dimensional surface. This idea revolutionized theoretical physics. If it's true for black holes, maybe it's true for all of spacetime. Perhaps our three-dimensional universe is actually a projection of information stored on a two-dimensional boundary far away, a cosmic hologram. In 2012, a group of physicists proposed something radical. Perhaps the event horizon isn't smooth and empty. Perhaps it's a firewall, a region of intense energy that incinerates anything trying to cross. This idea emerged from trying to satisfy three principles. 1. Information is preserved, quantum mechanics. 2. Hawking radiation is thermal, general relativity. 3. No drama at the horizon, equivalence principle. The problem: you can satisfy any two of these, but all three together seem impossible. Something has to give. The firewall proposal said, give up number 3. The equivalence principle, Einstein's insight that freely falling observers feel no gravity, fails at the event horizon. Instead, you encounter a wall of high-energy particles that destroys you instantly. This idea caused uproar. It violated one of general relativity's core principles, but it might preserve quantum mechanics and explain how information escapes. Most physicists rejected firewalls as too radical, but the debate revealed how deep the paradox goes. We still don't have a fully satisfactory resolution. A newer idea connects entanglement with space-time geometry itself. Physicists Juan Maldacena and Leonard Susskind proposed that quantum entanglement and wormholes are two ways of describing the same thing. ER equals EPR. ER refers to Einstein-Rosen bridges, wormholes connecting distant regions of spacetime. EPR refers to Einstein-Podolsky-Rosen pairs, entangled particles whose quantum states are correlated across distance. The proposal: when two particles are entangled, they're connected by a tiny wormhole, a quantum tunnel through space-time. The entanglement we observe is actually a geometric connection. If this is true, then information doesn't need to travel through space to escape a black hole. It's already connected to the outside through quantum wormholes, maintained by entanglement between Hawking radiation and the black hole's interior. Recent progress comes from studying simplified models of black holes. The Sachdev-Yekitaev (SYK) model describes a system of quantum particles with random interactions, a kind of quantum chaos. Remarkably, this model reproduces many features of black holes. It has similar entropy, it thermalizes information rapidly, and its dynamics match certain aspects of black hole physics. By studying how information scrambles in the SYK model, physicists have learned how black holes might preserve information while appearing to destroy it. The information isn't lost, it's scrambled so thoroughly that recovering it requires analyzing correlations between many particles at once. Imagine dropping a drop of ink into a turbulent ocean. The ink disperses, mixes, becomes invisible. But if you could track every molecule of water, you could, in principle, figure out where the ink went. Black holes are similar. They scramble information into quantum correlations so complex that practically recovering it is impossible. But fundamentally, the information persists. In 2019, physicists discovered what they call quantum extremal islands, regions where information is effectively stored during black hole evaporation. Using techniques from string theory and quantum gravity, they showed that at late times, you must include regions inside the black hole when calculating the entropy of Hawking radiation. These islands of spacetime contribute to the radiation's entropy in a way that allows the page curve to be satisfied. This is highly technical, but the upshot is, information does escape, encoded in subtle quantum correlations that become important only after the black hole has lost about half its mass. Another speculative idea. Perhaps information doesn't escape at all. Instead, it branches off into baby universes, tiny pocket universes that bud off from the black hole's interior and disconnect from our space-time. In this view, information is conserved globally across all universes, but lost from ours. The multiverse preserves unitarity, even if individual universes don't. This is even more speculative than other proposals, and most physicists are skeptical. But it shows how radical the solutions might need to be. In one of his last papers before his death in 2018, Stephen Hawking and colleagues proposed that black holes have soft hair, subtle quantum features that could encode information about what fell in. These features involve soft particles, particles with very low or zero energy, which don't affect the classical geometry but do carry quantum information. Perhaps these soft modes accumulate on the horizon, storing information that eventually escapes through Hawking radiation. The idea remains controversial and incomplete, but it represents one of the last contributions from the physicist who first identified the paradox. You might wonder, why does this matter? These black holes are distant, their evaporation takes longer than the age of the universe, and we'll never perform the experiments to test these ideas directly. But the paradox matters because it reveals a fundamental tension between our two best theories, general relativity and quantum mechanics. One must give way, or both must be subsumed into something deeper. Resolving the information paradox likely requires a theory of quantum gravity, a unified framework that describes spacetime at the smallest scales. String theory, loop quantum gravity, and other approaches all make predictions about how this works, and the black hole information paradox is one of the key tests. So as you rest, imagine information not as something solid and permanent, but as a pattern, a configuration of quantum states that can be scrambled, hidden, transformed, but never truly destroyed. When you fall into a black hole, you aren't lost. You're transformed, your information spread across the horizon, encoded in correlations so subtle they take billions of years to extract, yet preserved in the quantum structure of space-time itself. Nothing is ever truly gone. Everything that was still is, somewhere in the quantum tapestry, hidden perhaps but conserved, eternally part of the universe's total information content. Let that thought carry you gently forward as we explore what happens over the unimaginable timescales of black hole evaporation and why even these cosmic giants must one day fade into light. Chapter 7. Black Hole. Evaporation. Cosmic death in slow motion. Imagine the universe far in the future, trillions of years from now. All the stars have burned out, their nuclear fuel exhausted. No new stars form because the hydrogen and helium have been used up or locked away in stellar remnants. The galaxies themselves have drifted apart, carried by the accelerating expansion of space. What remains? White dwarfs cooling to black, neutron stars slowly decaying, and black holes, patient, immense, growing slowly as they absorb the occasional stray particle or photon from the cold vacuum around them. This is the black hole era, a phase of cosmic history that will last far longer than the age of the current universe, from about 10 to the 40 power years to 10 to the 100 power years and beyond. Black holes don't evaporate quickly. For a stellar mass black hole, the process takes about 10 to the 67th power years, vastly longer than the current age of the universe. For supermassive black holes, the timescale stretches to 10 to the power of 100 years or more. To put this in perspective, the universe is currently about 1.4 times 10 to the power of 10 years old, 14 billion years. A stellar mass black hole will survive for 1,000,000 trillion times longer than the universe has existed so far. During most of this time, the black hole emits Hawking radiation so slowly that the effect is negligible. The temperature of the radiation is far below the temperature of the cosmic microwave background, so the black hole actually absorbs more energy than it emits. Only in the far future, when the universe is cooled below the black hole's temperature, will evaporation begin in earnest. As a black hole loses mass through Hawking radiation, its temperature rises. Smaller black holes are hotter. This creates a feedback loop. As the black hole shrinks, it radiates faster, which makes it shrink faster still. In the final stages of evaporation, the process accelerates dramatically. A black hole that has spent trillions upon trillions of years barely changing will suddenly, in cosmic terms, begin radiating intensely, shrinking visibly, heating up until it glows white hot. In its last second of existence, a black hole releases as much energy as billions of nuclear bombs. It disappears in a blaze of high-energy particles, gamma rays, and gravitational waves, a brief, brilliant flash marking the end of a cosmic giant that once held the mass of stars or galaxies. What is the very last thing a black hole emits? Presumably a high-energy photon or particle that carries away the final bit of mass energy. But this raises a question. What happens to the singularity? If the black hole is completely evaporated, the singularity must have disappeared as well. But how? Singularities are supposed to be hidden behind event horizons. If the horizon evaporates away, does the singularity become naked, visible to the outside universe? Most physicists believe this doesn't happen. The cosmic censorship conjecture suggests that nature always hides singularities. Perhaps in the final moments, quantum effects smooth out the singularity before it can be revealed, or perhaps the last bit of the black hole vanishes before the horizon completely disappears. Another possibility, maybe black holes don't evaporate completely. Perhaps they leave behind remnants, tiny stable object with the mass of a proton or an electron, but containing all the information about what fell into the original black hole. These remnants would be incredibly dense, with event horizons perhaps only a few Planck lengths across, 10 to the negative 35 meters, the smallest meaningful scale in physics. If remnants exist, the far future universe would be filled with them. Countless tiny fossils of collapsed stars and galaxies, each one carrying the memory of everything that once fell into its parent black hole. This idea is speculative and raises its own problems, but it's one way to resolve the information paradox. The information isn't destroyed or even fully radiated away. It's compressed into stable remnants that persist indefinitely. As black holes evaporate, they add energy back to the universe in the form of Hawking radiation. But this energy is spread out, diluted by the expansion of space, becoming ever more diffuse. Eventually the universe reaches maximum entropy, a state where energy is so evenly distributed that no work can be done, no structure can form, no change can occur. This is called the heat death. In this state, the universe is cold, dark and empty, filled with nothing but faint photons from long evaporated black holes, neutrinos travelling through space, and perhaps quantum fluctuations in the vacuum. Some physicists speculate that even after heat death, the universe might fluctuate back into lower entropy states over unimaginably long timescales. Random quantum fluctuations could, by sheer chance, create pockets of order, perhaps even new universes budding off from the vacuum. But these are deep speculations, venturing far beyond what we can test or verify. Interestingly, Hawking radiation doesn't just destroy black holes, it also creates opportunities. The radiation includes all types of particles, photons, neutrinos, electrons, positrons, and even occasionally heavier particles like protons or quarks. In principle, if you could harness Hawking radiation from a small black hole, you'd have a nearly eternal energy source. A small black hole radiates intensely, and if you could maintain it at a stable mass by feeding it matter, you'd have a power source that lasts for eons. Of course, no such technology exists or is likely to exist, but it's fun to imagine advanced civilizations in the far future farming black holes for energy, keeping them at optimal sizes to extract power while staving off their evaporation. One wild idea, perhaps information escaping through Hawking radiation could, in principle, be used to reconstruct everything that fell into the black hole, including living beings. If you fell into a black hole, your information would eventually leak out over billions or trillions of years. A sufficiently advanced civilization, collecting all that radiation and analysing its quantum correlations, could theoretically reconstruct you, your memories, your personality, your physical form. This is the quantum resurrection hypothesis, more science fiction than science, but rooted in the principle that information is conserved. If your information escapes, then you, in some sense, persist, even if your physical body was destroyed near the singularity. After 100 years or so, even the largest supermassive black holes will have evaporated. The universe will contain no black holes at all, just faint radiation, cooling remnants if they exist, and the ever-expanding emptiness of space. This is not the end of time, but is perhaps the end of interesting structures. After this point, the universe becomes a cold, empty stage where nothing much happens, where change is measured in timescales longer than we have words for. It's humbling, contemplating these timescales. Our sun will die in 5 billion years. Our galaxy will collide with Andromeda in 4 billion years. But black holes will outlast all of this by factors of trillions upon trillions, patient, silent, slowly radiating into the void. So as you drift towards sleep, imagine a black hole in the far future, alone in a dark, cold universe, glowing faintly with Hawking radiation. It has outlasted every star, every planet, every galaxy. But it too is mortal. Slowly, imperceptibly, it fades. Photon by photon, particle by particle, it returns its stolen mass to the cosmos. One day, after eons beyond imagining, it releases its final particle and vanishes, leaving only a faint whisper of light travelling forever through the expanding void. Nothing lasts. Not stars, not galaxies, not even black holes. Everything that is will one day fade, returning to the quantum vacuum from which it came. And perhaps that's strangely comforting. Nothing to cling to, nothing to fear losing, only the gentle dissolution of all structure back into the formless potential from which it arose. Let that thought carry you softly forward as we explore the giants at the hearts of galaxies and what role these supermassive black holes play in shaping the cosmic structures we see today. Chapter 8: Supermassive Black Holes, Galactic Hearts. Every large galaxy, it seems, has a supermassive black hole at its heart. These aren't the stellar mass black holes formed from collapsing stars. They're millions or billions of times more massive, sitting at galactic centers like cosmic anchors around which stars orbit. Our own Milky Way harbors one, Sagittarius, a star, pronounced Sagittarius our star, a black hole with about 4 million times the Sun's mass, located roughly 26,000 light-years from Earth. Despite its enormous mass, Sagittarius A star is relatively quiet. It's not actively consuming much matter at the moment, but observations of stars orbiting it reveal its presence, stars whipping around an invisible point at incredible speeds, their orbits tracing out the gravitational influence of the black hole. In April 2019, the Event Horizon Telescope collaboration revealed the first direct image of a black hole's event horizon. The target was M87 star, the supermassive black hole at the centre of the Messier 87 galaxy, about 55 million light-years away. The image showed a bright ring of light surrounding a dark central region, the black hole's shadow. This shadow isn't the event horizon itself, but the region of space-time from which light cannot escape as seen from Earth. The bright ring is caused by photons orbiting the black hole in the photon sphere, the unstable region where light can circle the black hole before either falling in or escaping. It's fed by the accretion disk, a swirling mass of superheated gas spiraling into the black hole, glowing brilliantly as friction heats it to millions of degrees. In May 2022, the same team released an image of Sagittarius A star, our own galaxy's black hole. Though much smaller and closer than M87 star, Sagittarius A star was harder to image because the gas around it changes rapidly. The results showed a similar ring structure, confirming that black holes look the way general relativity predicts. One of the biggest mysteries in astrophysics is how supermassive black holes formed. Stellar mass black holes form from collapsing stars. We understand that process. But supermassive black holes are too big to have formed this way. Several possibilities exist. 1. Direct collapse. In the early universe, clouds of primordial gas might have collapsed directly into massive black holes without forming stars first. This requires special conditions, no nearby sources of ultraviolet light to break up the gas cloud, but it could produce seed black holes of thousands or millions of solar masses. 2. Runaway mergers. Maybe supermassive black holes grew from stellar mass black holes through mergers. In dense star clusters, black holes could merge repeatedly, growing larger with each collision. Over billions of years, this could build up a supermassive black hole. 3. Primordial black holes. Perhaps some supermassive black holes formed in the first moments after the Big Bang, during a phase of rapid inflation. These primordial black holes could have served as seeds, growing over time by accreting matter. 4. Exotic mechanisms. Some theories propose that supermassive black holes formed from the collapse of dark matter, or through other exotic processes involving physics beyond the standard model. Observation suggests that supermassive black holes existed when the universe was less than 1 billion years old, not much time to grow from stellar mass seeds. This is one of the major puzzles in cosmology. When matter falls toward a supermassive black hole, it doesn't plunge straight in. Angular momentum causes it to spiral, forming an accretion disk, a flattened structure of gas and dust rotating around the black hole. Friction within the disk heats the gas to millions of degrees, causing it to glow brilliantly in X-rays and other wavelengths. This is why we can see supermassive black holes, not directly, but by the light from their accretion disks. In some cases, powerful jets form, streams of particles accelerated to near light speed, shooting out perpendicular to the disk. These jets can extend for millions of light years, far beyond the galaxy itself, glowing in radio wavelengths. The mechanism that creates jets isn't fully understood, but it involves the black hole's rotation and magnetic fields threading through the accretion disk. The Penrose process and the Blandford-Zenajec mechanism are two theories that explain how rotational energy can be extracted from black holes to power these jets. When a supermassive black hole actively consumes matter, it can become a quasar, one of the most luminous objects in the universe. A quasar can outshine an entire galaxy, radiating more energy than 1 trillion suns, all from a region smaller than our solar system. Quasars are most common in the early universe, when galaxies were closer together and collisions more frequent. These collisions funneled gas toward the central black holes, feeding them and triggering intense emission. As the universe aged and galaxies spread apart, quasar activity declined. Most supermassive black holes today are relatively quiet, like Sagittarius A star, having consumed most of the nearby gas and settled into dormancy. Remarkably, the mass of a galaxy's central black hole correlates with properties of the galaxy itself. The mass of its central bulge, the velocity dispersion of its stars. This suggests that galaxies and their black holes co-evolve, influencing each other's growth. Black hole feedback is one mechanism. As a black hole accretes matter, the energy released can heat or expel gas from the galaxy, suppressing star formation. This prevents the galaxy from growing too quickly, and also starves the black hole, limiting its growth. This delicate balance helps explain why galaxies have the properties we observe. Without black hole feedback, galaxies might be much more massive, their centers filled with too many stars. The black holes regulate their own food supply, shaping the galaxies around them. Between stellar mass and supermassive black holes, there may exist a population of intermediate mass black holes, hundreds to thousands of solar masses, lurking in dense star clusters or wandering through galaxies. Evidence for these is tantalizing but not yet conclusive. Some globular clusters show hints of central black holes. Tidal disruption events and X-ray sources suggest the presence of intermediate mass black holes. And gravitational wave detectors have observed mergers of black holes heavier than expected from stellar collapse, possibly indicating an intermediate mass population. If these exist, they could be the missing link in understanding how supermassive black holes formed, seeds that grew over time, or the products of runaway mergers in dense environments. When galaxies merge, their central black holes eventually sink toward the center of the merged galaxy. If both galaxies had supermassive black holes, the result is a binary supermassive black hole system, two giants orbiting each other. Over time, these binaries lose energy through gravitational wave emission, their orbits shrinking until they merge in a colossal event that releases more energy than all the stars in the observable universe combined. We haven't yet detected such mergers with gravitational wave observatories. They're below the frequency range of current detectors like LIGO. But future detectors, like the space-based LISA mission, will be sensitive to these events, opening a new window into galaxy evolution. There's a puzzle with binary supermassive black holes. They should stall at a separation of about 1 parsec, about 3 light-years, and take an extremely long time to merge. This is called the final parsec problem. Gravitational waves carry away energy efficiently only when the black holes are very close. At larger separations, they rely on dynamical friction, interactions with stars and gas, to lose energy. But in the cores of merged galaxies, the supply of stars diminishes, leaving the binary stuck. Several mechanisms might overcome this: interactions with gas clouds, three-body encounters with stars, or changes in the galaxy structure. But the problem remains an active area of research. What would it be like to live near a supermassive black hole? Far from the event horizon, life might be surprisingly normal. The tidal forces at the horizon of a supermassive black hole are gentle, and the radiation from the accretion disk could be shielded. But the environment is harsh. Intense X-rays and cosmic rays from the accretion disk and jets would sterilize planets, stripping atmospheres and irradiating surfaces. Any life would need to be far from the active black hole, or protected by thick atmospheres and magnetic fields. In the movie Interstellar, the characters visit a planet orbiting close to a supermassive black hole, experiencing extreme time dilation. This is theoretically possible, but the planet would be bathed in radiation, making habitability unlikely. So as you rest, imagine the Milky Way's heart, a quiet giant, patiently waiting at the galaxy's center, shepherding stars in their orbits, a dark throne around which billions of suns dance. It's not a destroyer, not really. It's a sculptor, shaping the galaxy's structure, regulating star formation, binding the galaxy together through gravity's invisible threads. And one day, billions of years hence, it too will evaporate, slowly returning its mass to the universe in a faint glow of Hawking radiation. But for now it sits, watching, waiting, a reminder that even the darkest objects can be the hearts of creation. Let the thought carry you gently forward as we explore perhaps the strangest idea to emerge from black hole physics, the possibility that our entire universe is a kind of hologram and reality itself is a projection from a distant boundary. Chapter 9: The Holographic Principle, Reality as Projection. In the 1970s, physicist Jacob Bekenstein was puzzled by a simple question. Do black holes have entropy? Entropy measures disorder, the number of possible microscopic arrangements of a system. For ordinary matter, entropy is proportional to volume, A larger box of gas has more entropy than a smaller one, because it contains more molecules with more possible states. Bekenstein found something strange. Using thermodynamic arguments and Wheeler's black holes have no hair theorem, he showed that a black hole's entropy is proportional to the area of its event horizon, not its volume. This was weird. Information, we thought, was stored in three-dimensional volumes, but black holes seem to store it on two-dimensional surfaces. Stephen Hawking initially resisted this idea. How could a black hole have entropy without having internal structure? But when Hawking discovered black hole radiation, he found it had a temperature, confirming Bekenstein's insight. Black holes truly do have thermodynamic properties, and their entropy is indeed proportional to horizon area. The Bekenstein-Hawking formula. The formula is simple and elegant. C equals open parenthesis k times c cubed times, a close parenthesis divided by open parenthesis 4 times, g times h bar close parenthesis, where S is entropy, A is the horizon area, and the other symbols are fundamental constants. K, Boltzmann's constant, c, speed of light, g, gravitational constant, and h bar, reduced Planck's constant. In more natural units, it simplifies to S equals A divided by 4, where A is measured in Planck areas, about 10 to the negative 70 square meters. This means that the maximum entropy a region of space can hold is proportional to its bounding surface area, not its volume. This was shocking. It suggests that our three-dimensional universe might be describable by information on a two-dimensional surface. In the 1990s, Gerard 't Hooft and Leonard Susskind independently proposed the holographic principle. The information content of a region of space can be fully encoded on its boundary. Think of a hologram, a two-dimensional surface that contains enough information to reconstruct a three-dimensional image. The holographic principle says the universe works similarly. The three-dimensional spacetime we inhabit is encoded on a two-dimensional boundary at the edge of the universe. This doesn't mean the universe is literally flat. It means that everything happening in a volume of space can be equivalently described by degrees of freedom on the surface bounding that volume. Why would this be true? Because black holes set the limit. If you try to pack too much information into a region, it collapses into a black hole, and black holes have entropy proportional to surface area. So the maximum information any region can contain is limited by its boundary, not its volume. The most concrete realization of the holographic principle comes from string theory, through something called the ADS/CFT correspondence, discovered by Juan Maldacena in 1997. ADS stands for anti-de Sitter space, a kind of negatively curved space-time, like a saddle shape extended to many dimensions. CFT stands for conformal field theory, a quantum field theory living on the boundary of that space, with one fewer dimension. Maldacena showed that a gravitational theory in ADS space is exactly equivalent to a quantum field theory on its boundary. Everything happening in the interior, black holes forming, particles moving, space-time curving, can be perfectly described by a theory with no gravity, living on a lower dimensional boundary. This was revolutionary. It provided a concrete example where gravity and space-time are emergent, arising from quantum entanglement and information in a boundary theory. If the holographic principle is true, space-time might not be fundamental. It might emerge from something deeper, perhaps from quantum entanglement between degrees of freedom on the boundary. Mark van Ramsdonk and others have shown that in the ADS/CFT framework, entanglement in the boundary theory literally sews together space in the interior. When quantum states on the boundary are entangled, the corresponding regions in the bulk spacetime are connected. break the entanglement, and space-time itself disconnects. This suggests that space-time is a kind of illusion, a higher-level description arising from quantum information at a more fundamental level. Just as temperature emerges from the motion of molecules, space-time might emerge from the entanglement of quantum bits. The firewall paradox emerges partly from holographic considerations. If all the information about a black hole's interior is encoded on its horizon, then Hawking radiation must carry that information away. But for the radiation to be entangled with the black hole's interior, preserving information, it can't also be entangled with earlier radiation, which would make it thermal. This double entanglement seems impossible, a violation of quantum mechanics' monogamy of entanglement. Something has to give. Either information is lost, or the horizon becomes a firewall, or our understanding of space-time breaks down in some other way. The holographic principle suggests a resolution. Perhaps there's no interior at all, at least not in the sense we imagine. The black hole's interior is a holographic projection from the boundary, and falling in is a description from one perspective that doesn't quite match the boundary description. Leonard Susskind's black hole complementarity idea fits naturally with holography. From outside, the black hole is described holographically. All information is on the horizon and leaks out through radiation. From inside, there's a smooth space-time where you can fall toward the singularity. These are two complementary descriptions of the same reality, like wave and particle descriptions in quantum mechanics. Both are valid, but they can't be directly compared because no observer can see both simultaneously. If the holographic principle is truly fundamental, does it apply to our universe? Is there a two-dimensional boundary at the edge of the observable universe, encoding everything that happens within? Some cosmological models suggest this might be true. In particular, the De Sitter space model, describing an accelerating, expanding universe like ours, might have a holographic boundary. If so, everything you experience, every thought, every sensation, every event in your life is encoded as information on a distant two-dimensional surface. You and the entire three-dimensional space you inhabit are projections from that boundary. This doesn't mean you're not real, just that your reality has a different fundamental description. The hologram and the three-dimensional image are both equally real. They're just two ways of describing the same information. The holographic principle is one of the few concrete clues we have about quantum gravity. It tells us that space-time has finite information capacity, that dimensionality might be flexible, and that gravity and quantum mechanics are deeply connected. String theory, loop quantum gravity, and other approaches to quantum gravity take the holographic principle seriously, using it to constrain possible theories and guide research. If we ever develop a complete theory of quantum gravity, the holographic principle will almost certainly be a central feature, a guiding star that helped us navigate the deep waters between relativity and quantum mechanics. Imagine, just for fun, that you're a character in a sophisticated computer simulation. The simulation runs on a two-dimensional grid, like pixels on a screen, but it creates the illusion of a three-dimensional world. Are you any less real? Does it matter whether your experiences are generated by three-dimensional brain chemistry or by information processed on a two-dimensional substrate? The holographic principle suggests something similar. We might be patterns of information encoded on a distant boundary, experiencing ourselves as three-dimensional beings moving through space and time. But the richness of our experience, the reality of our thoughts and feelings, is undiminished. We are not diminished by being holograms. If anything, we're elevated. We're part of a cosmic information structure so profound that space-time itself emerges from our entanglement with the rest of the universe. As you drift into rest, imagine yourself not as a solid object in space, but as a pattern, a holographic projection from a distant boundary, your three-dimensional existence encoded in quantum information on a two-dimensional surface at the edge of the cosmos. You're still real, your experiences still matter, but you're also part of something larger, something more beautiful, a universe where information is fundamental, where space-time is emergent, and where reality itself is a hologram painted in quantum states on the cosmic horizon. Let that thought carry you softly forward as we reach the final chapter. What it would feel like to fall forever, to experience the eternal now at the event horizon, where time dilates toward infinity and the universe ages eons in seconds. Chapter 10. Falling Forever. The eternal now at the horizon. We return now to the central paradox of black holes, the clash between what an outside observer sees and what a falling observer experiences. From outside, you never quite reach the event horizon. Time slows asymptotically. Your image freezes, redshifts, fades. You become a permanent ghost at the boundary, eternally approaching but never crossing. But in your frame, you cross smoothly. Time flows normally. You pass through the horizon in finite seconds or minutes, continuing inward toward the singularity. Nothing special marks the crossing. No wall, no sensation, just the inexorable pull of gravity. Both descriptions are correct. Time is relative. There's no universal now that all observers share. The universe allows both stories to be true simultaneously, because they can never be directly compared. Imagine you're falling toward a supermassive black hole, one large enough that tidal forces at the horizon are gentle. What do you see and feel? Initially, far from the horizon, the black hole appears as a dark sphere against the stars. As you fall closer, it grows, filling more of your view. The stars behind you, in the direction you're falling from, appear to bunch up and blue shift, their light compressed by your motion and by space-time curvature. The stars ahead, toward the black hole, spread out and redshift, their light stretched. The black hole itself remains dark, but you can see light bending around it, the photon sphere, where photons orbit the black hole before either escaping or falling in. As you approach the horizon, the view becomes increasingly distorted. The entire external universe seems to compress into a shrinking cone behind you, blue shifting toward higher energies. In principle, you might see the future of the universe flash before you. Stars evolving, galaxies colliding, the cosmos aging in compressed time. This is because light from the future can catch up to you as you fall. From your perspective, the universe outside is speeding up, aging rapidly, perhaps showing you billions or trillions of years of cosmic history in your final moments. You cross the event horizon. Nothing dramatic happens. There's no surface, no warning. You're simply inside now, with no possibility of return. If you looked back, would you see the horizon? Not as a bright line or surface. Instead, you'd see the entire universe compressed into a bright point behind you, blue shifted to intense gamma rays. This white hole appearance represents all the light that ever fell into the black hole from your perspective, compressed by space-time curvature. Ahead lies only darkness, the singularity's future, inevitable and approaching. You're no longer falling through space, but moving forward through time, with the singularity as a moment in your future rather than a place in space. As you approach the singularity, tidal forces grow. Even in a supermassive black hole, you eventually reach a point where the gradient is too extreme. You begin to stretch, first gently, then violently. Your feet are pulled harder than your head. Your sides are compressed inward while your length extends. The spaghettification we discussed earlier becomes unavoidable. Before you reach the singularity, you would likely be torn apart, your body elongated into a stream of atoms, then particles, then perhaps something even more fundamental. And then, we don't know. The singularity is where our theories fail, where infinity emerges in the equations, and where quantum gravity must take over. Perhaps you're not destroyed but transformed, your information preserved in the quantum structure of spacetime itself. Meanwhile, to an observer outside, none of this has happened. You're still approaching the horizon, frozen in time, your image fading but never quite disappearing. Every photon you emit takes longer and longer to escape the black hole's gravity, redshifting until it becomes undetectable. In this sense, you never truly cross from the outside perspective. You remain eternally at the boundary, a permanent part of the black hole's horizon, your information encoded on its surface as the holographic principle suggests. This is the strange duality of black holes. You both cross and don't cross. You both fall and freeze depending on perspective. Reality at the event horizon is paradoxical, refusing to be pinned down to a single narrative. The horizon represents a kind of eternal now, a boundary where time dilates infinitely, where the concepts of before and after blur into something ambiguous. From outside, the horizon is a frozen moment, a surface where nothing ever quite happens but everything is preserved. From inside, it's a smooth transition, a moment passed in finite time, leading inexorably to the singularity. Perhaps this duality reflects something deep about the nature of time itself. Perhaps time is not a single universal flow, but a collection of perspectives, each equally valid, each telling a different story about the same events. The horizon is where these perspectives diverge most dramatically, where the relativity of time is pushed to its extreme. It's a boundary not just in space but in the structure of reality itself. Black holes, in the end, reflect back to us the mysteries of existence, the nature of time, the structure of space, the meaning of information, the relationship between quantum mechanics and gravity. They're cosmic mirrors, showing us the limits of our understanding and hinting at deeper truths. We cannot see inside them, cannot rescue what falls past the horizon, cannot escape their pull once we cross the boundary. And yet, through mathematics and observation, we've learned to describe them, to predict their behavior, to glimpse the strange physics at their edges. Every question we answer about black holes raises new questions. Every paradox we resolve reveals deeper paradoxes. They are physics sphinx, posing riddles that test the limits of human knowledge. If you could somehow survive falling into a black hole, could withstand the tidal forces, could experience the crossing without being destroyed, what would you learn? Perhaps you'd learn that time is not what it seems, that the present is more flexible than we imagine, that the universe can be viewed from perspectives so different that they seem contradictory yet are both true. Perhaps you'd learn that destruction is transformation, that nothing is truly lost, that information, and therefore identity, persists even in the most extreme conditions. Perhaps you'd learn that boundaries are not endings, but transitions, that horizons mark not the edge of existence, but the beginning of something we cannot yet describe. So, as you settle into the deepest rest, imagine yourself at the event horizon, not falling, not frozen, but suspended in the eternal now, where past and future collapse into a single timeless moment. Behind you, the universe ages, stars dying, galaxies fading, eons passing in seconds. Ahead, the singularity awaits, not as destruction but as transformation, as the ultimate unknown. You are both here and there, both falling and frozen, both particle and wave, both observer and observed. You are the universe contemplating itself at the edge of its own mystery, where space-time curves into infinity and all our theories dissolve into wonder. And perhaps that's fitting. Perhaps the universe needs places like this, places where knowledge ends and awe begins, where the equations give way to experience, where the only answer is to let go and fall forever into the eternal now. As we reach the end of this cosmic journey, take a moment to let the vastness settle. We've travelled from event horizons to singularities, from Hawking radiation to holographic principles, from the smallest quantum fluctuations to the largest structures in the cosmos. We've explored where space-time dies, and we've seen that even black holes, the universe's most absolute endings, are also beginnings, slowly returning their substance to the cosmos through the patient glow of quantum radiation. If this exploration has stirred something within you, a sense of awe, a deeper curiosity, or simply peace in contemplating the universe's most profound mysteries, I invite you to linger in that feeling. Subscribe to Sleep Entangled for more journeys through the cosmos where physics and philosophy merge into tranquil voyages. Like this video if it resonated with you, and share it with fellow seekers who gaze at the night sky and wonder what lies beyond. This is Sleep Entangled, where space-time bends and wonder remains eternal. Until we meet again at the next cosmic horizon, rest deeply in the knowing that even the darkest mysteries can illuminate the mind. Because in the end, black holes teach us that nothing, not matter, not energy, not even information, is ever truly lost. Everything transforms, everything persists, everything returns in time to the universe that birthed it. May your dreams be filled with stars collapsing and space-time dancing, and may you wake to a universe more mysterious and beautiful than when you closed your eyes.